Hello, students. Have you ever wondered why metals like gold and copper are so dense and shiny, while others like glass are comparatively lighter and irregular? The secret lies in how their atoms are packed inside. During the formation of a crystal, atoms or ions arrange themselves as closely as possible, leaving minimum empty space. This state of maximum density is called close packing. But the interesting part is that not all crystals achieve the same efficiency because their particles differ in size and shape. Still, no matter the type of particle, nature always pushes them toward the closest possible arrangement. Today, we'll explore how particles achieve this remarkable order and how the empty spaces, or voids, play a vital role in crystal structures.
Let's begin by visualizing how spheres of equal size arrange themselves on a flat surface. If you place marbles in rows and columns, one above the other, you'll get what is called square close packing. In this arrangement, each particle touches four others, two in its row and two in the column. But nature always finds more efficient ways. If you push the second row slightly into the gaps of the first, you get hexagonal close packing in 2 dimensions. Here, each particle touches 6 neighbors. While square packing only achieves about 52% efficiency, the hexagonal arrangement reaches around 60%, showing that a simple shift leads to greater density. If you imagine this, it's like arranging oranges neatly in a box versus randomly stacking them. But even in efficient packing, there are always gaps left behind. These gaps are called voids. In 2-dimensional hexagonal packing, the voids are triangular in shape. Some are labeled as type A and others as type B, arranged alternately in the structure. These triangular gaps may look small, but they are the building blocks of higher, 3-dimensional arrangements. Essentially, voids are the secret pockets inside a crystal that later decide how cations and anions will fit in ionic solids. Now let's add another layer and step into 3 dimensions. Imagine taking the hexagonal layer of spheres and placing another on top. If the second layer sits exactly over the first, the arrangement is less efficient. But if it is shifted so that the spheres of the second layer fall into the voids of the first, you get a compact arrangement. If the third layer repeats the first, the sequence becomes a bar, which is known as hexagonal close packing. If the third layer is placed differently, covering the gaps of both A and B layers, the sequence is ABC, known as cubic close packing. Both these forms are highly efficient, with a packing efficiency of around 74%, which is the maximum possible. This is why many metals like zinc, cadmium, copper, silver, and gold crystallize in these structures. In crystal chemistry, another important property is the coordination number, meaning the number of nearest neighbors a particle touches. In both hexagonal and cubic close packing, every sphere is surrounded by 12 others. This coordination number of 12 explains the high density and stability of metals like magnesium, aluminium, and gold. On the other hand, in a body-centered cubic arrangement, each sphere is in contact with only 8 neighbors, leading to a lower packing efficiency of about 68%. So, while HCP and CCP are the most tightly packed, DCC offers a less dense but still highly ordered structure. When we move to 3 dimensions, the empty spaces or voids become even more fascinating. 2 main types appear: tetrahedral voids, where a small particle can be surrounded by 4 larger spheres, and octahedral voids, where it is surrounded by 6. The number of tetrahedral voids is always double the number of spheres, while the number of octahedral voids equals the number of spheres. These voids are not wasted space. In fact, they are the reason ionic compounds exist in nature. Smaller cations tuck themselves neatly into these voids formed by larger anions, giving us stable compounds like sodium chloride and zinc sulfide. Now comes the mathematical beauty of it. Whether an ion will fit into a void depends on its radius ratio. For a tetrahedral void, the ratio of the radius of the smaller ion to the larger ion is 0.225. For an octahedral void, it is 0.414. For example, in sodium chloride, chloride ions form a cubic close packing, while sodium ions with the correct radius slip perfectly into the octahedral voids. If the radius ratio doesn't match, the smaller ions cannot occupy that void without disturbing the lattice. This simple rule of geometry beautifully explains why salts adopt specific structures. Here's where close packing connects directly with chemical formulas. If all tetrahedral voids are filled by cations, the resulting formula becomes AB. If only half the octahedral voids are filled, the formula becomes AB. A real example is zinc blende, where sulfide ions form a close-packed lattice, and zinc ions occupy half of the tetrahedral voids, giving the formula ZnS. Similarly, in sodium oxide, oxide ions form CCP, while sodium ions occupy tetrahedral voids. Thus, the beauty of nature is that something as simple as filling empty spaces explains the precise stoichiometry of compounds. So, let's quickly revise. Close packing is nature's way of arranging particles to minimize empty space and maximize stability. We saw 2D arrangements like square and hexagonal packing, then extended them to 3D structures like hexagonal and cubic close packing. We explored coordination numbers, the role of tetrahedral and octahedral voids, and how radius ratios decide which ions occupy which spaces. Finally, we linked void occupancy to the actual formulas of compounds like NaCl, ZnS, and now, isn't it fascinating how the invisible geometry of atoms dictates the very shape of crystals we see around us? I hope now you can appreciate why metals are so dense, why salts are so stable, and how solid-state chemistry connects with materials in our daily lives. See you in the next session, where we'll dive even deeper into the microscopic order of matter.